Perfect. So we are back on homework 9, questions 3 and 4, and I got the iPad working this time, and now I can draw down here. So for question 3, let's just read through it together and talk about the important things that are going on here. So it says, design a truth table and logic circuit. So we're doing two things. We're going to design a truth table and logic circuit to detect overflow of a 2's complement number addition, of 2's complement addition, a plus b is equal to c. So let's write that down. A plus b is equal to c. And the output is overflow. In other words, the output overflow goes high when we experience the state that can never happen. Remember that a 0 represents a positive number and a 1 represents a negative number, so let's write that down. 0 is equal to positive numbers and 1 is equal to negative numbers. So we can never get a negative value if we are adding two positive values. Similarly, we can never get a positive value if we are adding two negative values. So that last part is just talking a little bit about what overflow is. So let me explain that first before we dive into this one. So what you learned from problem 1 is that if you have 4 bits, then the range of 4 bits is -8 to +7. And so what ends up happening is if we add two numbers together, we'll put a little addition sign there, we'll do binary addition. Sometimes if we add two numbers together, they can leave this range. So an example of that would be adding the number 4, so that's 4 on the top, with the number 5. So if we add 4 and 5 together, we should get 9, but what we'll notice is 9 is bigger than 7, so we'll probably get something wrong. So let's do this math. So 0 plus 1 is 1, 0 plus 0 is 0, 1 plus 1 will become 0 and will carry a 1, and then 1 plus 0 will equal a 1. And what you'll notice is in binary, this represents 9. But because we're working in 2's complement numbers, we have to remember that this represents -8, where this one is 4, 2, and 1. So this actually turns into -7, which is clearly not the 9 that we were looking for earlier. But unfortunately, computers don't know what the answer should be. So there has to be a way for them to detect when things like this happen, when we add two numbers together and something goes wrong. And the way that they detect that is by checking the signs of the inputs and comparing that to the outputs. And by that I mean, if we add two positive numbers together, so a positive plus a positive, and if we get a negative number, that means that we had overflow, and I'll abbreviate that as OF. Similarly, if we have a negative plus a negative, and we get a positive, that will also indicate overflow. So if we ever find those situations, that means that overflow has occurred, and that's a good time for a computer to check to see if something has gone wrong, because otherwise the computer would have no idea if the answer -7 was correct, or if they should recompute and get to -9. So for this problem, we have to design a truth table and a logic circuit. So let's start with the truth table, and I'll switch to red for this. So for the truth table, we have inputs A, B, C, and our output column will be overflow, and that will go high anytime we detect overflow. So let me fill in this truth table really quick. And just so you know, remember that all truth tables with 3 inputs should be set up this way with the inputs. So for this, we know that we are doing, let's change to blue, we're doing A plus B is equal to C. So, and we know that zeros are positive numbers. So if we look at this first row, this means that we have a positive number added with a positive number, and that equals a positive number. So an example of that would be 1 plus 2 is equal to 3, and 3 is not outside of our range of +7, so we know that that is not a time where overflow would occur. So we'll put a 0 there. If we look at the next row, what we'll notice is we'll do a positive plus a positive, and that equals a negative. Let me change this one to a positive sign up here because I wrote equals before. So a positive plus a positive is equal to a negative. And what we'll notice is that was one of our two cases in which overflow occurs. And clearly a positive plus a positive is equal to a negative, or should not be equal to a negative, and therefore we can put a 1 in this row indicating that there is overflow. So if we look at the next row, we'll see that we have a positive plus a negative is equal to a positive. An example of that would be 1 plus negative 3 equals 3 plus negative 1 is equal to positive 2. And none of those numbers leave our range, and we can say that that does not have overflow. So I'll let you go through the rest of this and find the other case of overflow, because remember, there's only two cases, so that means that there should only be one more 1 to put into that. So we already found 1, and you have to find the spot where there's another 1, and it should match the other case that we identified from earlier. So now, moving on to the logic gate circuit, if you want to draw a logic gate circuit, what we're going to do is I'm going to make a separate truth table that is not specific to this problem, and I will do that one, and that should give you enough information to go back and complete this one. So give me 1 second, I will draw a truth table, and you can skip through this part while I'm drawing it, and then once I get to the logic gates, you can catch back up. So here I'm just going to pick some random outputs. Let's say we have a 1 here, here, and the rest are zeros. That sounds good. I'm going to only choose 2 rows because yours will only have 2 rows as well. So for now, I can start by writing the Boolean logic equation. So I can say f is equal to, and we know that f, let me switch to blue, f is equal to, we only have 2 cases where f is positive, so f will be equal to 2 things, and this first one will be a naught, b naught, c naught, because these are all zeros, and or it can be equal to a naught, b, c naught, because we have 2 zeros and a 1 at b, so b will not be negated. And so you can write this equation for the previous problem if you want to. You don't have to, but it's good practice. So going from this to a logic gate circuit, what we'll notice is we have 2 things that are being ORed together. So that plus sign is an OR gate. So we're going to need an OR gate. So let's draw an OR gate. And our output will be equal to F. And what's going to happen is those 2 inputs of the OR gates are going to be equal to 2 different things. And let's do this in green. So let's start with this one. So this is an AND, because they're being multiplied. This will be an AND gate, and it'll have 3 inputs. And there'll be another AND gate on this one. Oops, sorry about that. Let's draw a better AND gate. And this one will also have 3 inputs. And so let's call those inputs A, B, C, A, B, C. And because the first one has negation symbols on all of them, we would add little bubbles to those to show that those are negated. And similarly, we would add bubbles to this one and this one, but making sure to leave B not negated, because in the equation, it's the only one that's not negated. And what we can find from this equation and the logic gate circuit is we have 2 3-input AND gates that are being ORed together. And if we look at our logic gate circuit, we have a 3-input AND gate, another 3-input AND gate, and those are being ORed together to produce our output F. So hopefully that is enough information for you to complete the logic gate circuit for problem number 3. So moving on to question 4, This one is not super complicated. So it says, what Boolean logic function does a 1-bit by 1-bit, or what does a 1-bit by 1-bit binary multiplication? So let's just separate ourselves from this previous work, and let's move on to number 4. So we know all we're doing is a 1-bit by 1-bit multiplication. So let's do 0 times 0, that's equal to 0. Let's try 0 times 1, that's equal to 0. And let's try 1 times 0, it's also equal to 0. And 1 times 1, which is equal to 1. And some of you may be catching on by now, but if I drew something like this, and then put some variables on top, you might be seeing something similar to what you've done before. And so the question is asking, well, what Boolean, it says in the question, it says, what Boolean logic function? And so the options for that are AND, OR, NAND, NOR, XOR, or XNOR. So those are your 6 options. And so now all you have to do is look at what this is and identify, okay, what does this make, or which one of these 6 would make a column that looks like this? And hopefully you can figure that one out. If not, you can scroll through the notes until you find the slide that has truth tables on it, and you find the output column that looks like this, and that should help you get through it. Anyways, if you have any questions, you can always email me or any of the other TAs or Dr. Beard, and they will help you through the rest of the homework assignment. Thanks so much.